Hello and welcome back to Guillotined 18th Century Chemist Theater. In our last adventure, we talked a little bit about the units of pressure and how we measure it using barometers, manometers, tire gauges, etc., etc. And pressure is absolutely a fascinating concept, the idea of the little forces against the side of the container. But where pressure really becomes interesting is where you have differences in pressure. Because what's going to happen is the pressure is going to move to try to equalize that pressure difference. And the ramifications of that lead to a lot of neat examples. And so let's first talk about the idea of a pressurized cabin. When we travel around, oftentimes we are traveling around in places where the atmospheric pressure is not conducive to our health, like spaceships or airplanes. And if those were ever breached, then the atmospheric pressure is going to attempt to equalize with the pressure inside. Now, when you're driving down the street in a car or a bus and you open a window, this isn't a big deal, because the pressure on the outside of the bus is the same as the pressure inside the bus, so nothing really happens. But it's different if you're underwater or if you're up in the air. Now, underwater, I understand that we're dealing with water and not a gas. But nonetheless, it's going to be a lower pressure on the inside, and the air is going to rush, while the air and the water are going to rush in to equalize the pressure. So being in a submarine can be pretty dangerous because that water is going to have a lot of force to get in there and try to equalize the pressure. Now, but more relevant to this, though, is the idea of a lower pressure on the outside. So if you're up in the air, up high in the atmosphere, there's less atmospheric pressure. And so if there's a breach in the hull, then air is going to rush out of the hull in an attempt to get pressure equal on both sides. Now, again, the ship is much smaller than the atmosphere, or the spaceship is much smaller than space. And so the air will rush out until it equals atmospheric pressure. In a movie, you might see, a hole in the side of an airplane or a spaceship, and people, getting strained out the hole or something like that, bent in half. That wouldn't happen. 1 atmosphere of pressure isn't enough to rip you in half or anything like that. But air will rush out. The big danger of a depressurized hull is the fact that if you're up in the high atmosphere, isn't necessarily that you're going to get sucked out. Notice I don't say sucked out, because that kind of gives you the opinion that, something's like pulling it out. It's getting sucked out. That's not really what's happening. Air is pushing out to try to equalize. And if you're in the way, you might get pushed out of the hole too. But if you can hang on, eventually the pressure will equalize, and now you're dealing with lower atmospheric pressure on the inside and the outside. That's the whole reason it was pressurized in the first place. And so you're going to deal with the fact that you're going to have less oxygen or no oxygen. If you're in space and the hull is ruptured, again, all of the air in the ship is going to rush out, and eventually the atmospheric pressure inside the spaceship is going to be zero. So, in any movie, there's usually they open the airlock to try to get rid of some monster that's in the ship. And if the monster can just hold on, eventually the pressure will equalize, and then it can have its way with the ship. Now, if it needs to breathe oxygen, it's in as much trouble as you are. But that's the idea, is the air is rushing out of there to try to equalize pressure, and hopefully, that monster gets carried out with everything else that gets rushed out to try to equalize pressure. But if the monster doesn't have to breathe oxygen, now you're in real trouble, because it'll just wait till it equalizes and just climb right in. So think about that next time you open the airlock to try to get rid of a monster. Breathing is sort of like an airlock, I guess. A lot of people, when you think about breathing, you think about sucking in air, like you have some massive power over the atmosphere. But breathing is actually a much more humbling experience when you think about it. If you just sit there with your mouth open, atmospheric pressure is the same inside your lungs as outside your lungs. But if you want to breathe in, what do? You expand your lungs. Your diaphragm expands your lungs, creates a greater volume, and that instantly creates a lower pressure inside your lungs. And we'll talk about that gas law later. And so what happens is the atmosphere rushes into equalized pressure, and once the pressure has been equalized, air stops rushing in. And so you can try to expand your lungs a little bit more, and then all of a sudden you'll notice that more air rushes in, and again and again and again, and try to expand your lungs as much as you can. Air will continue to rush in, and with it comes the oxygen, and that's the whole point. Oxygen diffuses across your lung into your blood, and that's all good. And then what's also happening is carbon dioxide is then diffusing into your lungs, or effusing into your lungs. And so when you want to get rid of that, what do? Well, you create a higher pressure inside your lungs, and you do that by compressing your lungs, and then you create a smaller volume, instantaneously a higher pressure, which instantaneously equalizes with the outside. So go ahead and breathe out. Now again, you're not the atmosphere isn't sucking that air out of you. You're pushing that air out. You're creating a lower pressure, and the air is rushing out in an attempt to equalize, just like if there was a hole in the spaceship. And eventually it'll equalize with atmospheric pressure. So if you were in space, at the first opportunity, the air would rush out of your lungs, and then even though you could, move your lungs in and out, you could expand and contract them, you would not feel the sensation of air rushing into your lungs because there is no air in space. But you could still breathe, but you just wouldn't be moving any atmosphere around. And so if the atmosphere were to double or triple, air would rush into your lungs also to equalize. Or if the atmospheric pressure went down, air would rush out of your lungs. So you have a lot less control over breathing than you think. It really depends on the atmosphere. And you create opportunities where you invite the atmosphere in and the oxygen, and then you try to encourage it to leave your lungs by creating a higher pressure so it rushes out. But again, you don't suck air into your lungs. So hopefully that's a little bit of a paradigm shift in the way you think about that. Which leads to the laziest way to consume food, and that's through a straw. So if you think about a straw, again, we've talked about it before when we started talking about barometers. And again, you could call it a cheap barometer, but really it's in actuality, it's more like a cheap manometer because there's always going to be pressure on both sides of a straw. But if a straw is just sitting there, you might have a little capillary action, but nothing's going to happen. Nothing's going to rise up the straw. But if you create a lower pressure inside, what's going to happen is that all of a sudden the atmosphere can start pushing the liquid up the straw. So here comes Puzzle Cow. Puzzle Cow is going to take a drink. Puzzle Cow expands the lungs, and with it, it creates a lower pressure. And so just like a barometer, the liquid's going to get pushed up the column to try to equalize. Now, hopefully, you are able to create low enough of a pressure so that the atmosphere pushes it all the way up to your mouth. Hopefully, you don't pull it into your lungs. That would be bad. You don't want to choke on it. But that's how straws work, which is kind of a neat idea, which means that there's a limit to how tall a straw can be. Atmospheric pressure can push water up a straw about 30 feet. And so if you tried to drink out of a 31, 32-foot straw, you would not be able to do it. Because even if you were to create a total vacuum in that straw, the atmosphere can only push it up so high. So in the summer, I used to work at a carnival, and we used to have a big straw like this. And people could try to suck the straw, And we were actually at the top of the old potato sack slide. And people would have their own cap. You wouldn't all be sucking off the same straw. And so, people could try to suck on that straw as hard as they wanted to, but it doesn't matter. Even if they could create a perfect vacuum inside their lungs, which they couldn't, they would never get the water out of the straw. So you charge a couple bucks a shot, and then you collect money all day, which is great until somebody who understands science comes up, and then it's time to pull up stakes and leave town once people realize there's no way to ever get the water out of that straw if it's 30 feet. And so, so if you can think about straws in space, it's very interesting. Drinking straws will not work in a vacuum because there's no atmospheric pressure to put it up. In fact, if you were to put your mouth on a straw in a vacuum, air would rush out of your lungs, and then it would bubble out of whatever liquid the straw was in until it equalized pressure with a vacuum. But that doesn't mean you can't use a straw in space. You could actually use it in a spaceship. And it would probably work better than Earth because you wouldn't necessarily be dealing with gravity, which is a neat idea. So you could actually, in theory, you could have an infinite straw. You could have a straw miles and miles and miles long in space because as long as there was an atmospheric difference, the liquid would move up the straw in an attempt to equalize pressure. So there it is. That's my contribution to humanity is the infinite straw. As long as you're not dealing with gravity and you have a pressure, you can move liquid along a straw like that. So you're welcome, civilization. So anyway, that's all we're gonna do for today. After this, we'll start getting into what makes water boil, which is fascinating, and vapor pressure, which is also fascinating. And after that, we'll roll into gas laws and start getting into some math. Anyway, I hope you enjoyed this lesson. I certainly did. Thanks for watching, and have a great day.